Hi, my name is Kyle James and this is my how-to video. In this video, I'm going to walk you through what I've done this year in my project creation. My project came from the idea that technology should be integrated as much as possible throughout sports, and for as little as possible. Instead of a $30,000 motion tracking system, I used sensors and what I had around the house. I hope you like my video. Thanks for watching. The first thing I made was the base of my project. I used 4 2-foot by 2-foot plywood pieces and nailed them together with wood glue in between the boards to tighten the seal. I then created the swivel to mount the hitting arm onto. The idea for the swivel came up as an idea in a conversation between a teacher and I, who I don't have this year but knows a lot about the subject. He was sitting spinning in a chair and then jumped up and said, "I got it! Use the chair." So I did. First I took out the wheels, then I took off the back seat. So it was just the base, the bottom cushion, and there was a metal connector that slid back and forth between the swivel and bent upwards, connecting the base to the back cushion. The only problem was that this metal connector had welded on rungs so it couldn't come off. I then went and got a hacksaw and cut off the metal connector. The only part left, the swivel, was screwed into the seat. So I unscrewed it from the seat, drilled holes in the top of the base I just made, and screwed the swivel in. I then purchased a hitting stick online to attach to the swivel. Before attaching the hitting stick, I first hacksawed off 2 of the 5 legs to the chair to make it more open and get rid of the unused arms. Now it looked like a stick man with no head or arms. I attached the hitting stick to the top of the solitary leg of the chair and used electric tape to hold it on. I then pre-drilled 2 holes onto the top left and right corners on one side of the base and 2 more in the backs of the other legs of the chair. I then screwed hooks into all 4 of these holes. On these hooks, I have 4 large rubber bands going diagonally each way, so that the hitting swivel comes back to set for the user in the same spot every time. Once I had created this, I went on to purchase what I would need for the technical side of my project. I ordered 2 sensors, a triple-axis accelerometer breakout and a triple-axis accelerometer and gyro breakout for $60 from sparkfun.com. Once I had these, I also ordered a starter kit from Arduino, which came with resistors, LEDs, jump wires, charging cables, USB cables, and a breadboard for $65, which puts my project at a total of $125 since I got the wood from scrap at the hardware store and the chair for free. The next part of the project was to wire everything all together so it works in a symphony of harmony. I first placed 2 buttons onto the breadboard, one at the very bottom in the middle of the breadboard and another 4 rows above that. I then connected resistors to each of the pins next to them and the other side to the ground. Also, on the other side of the buttons, I placed a wire next to each in line with the resistor. I plugged these wires into pins 4 and 6 on the header. The way the button works is the same as everything else. A change in electric current creates a serial entry, and that serial data is specific to a command written in the code. Specifically, the button has a resistor next to it, which provides a low voltage through the breadboard and to the wires connected to pins 4 and 6 when the button is not being pressed. But when the button is being pressed, it allows a larger flow of electricity and therefore provides a high voltage to the wires attached to pins 4 and 6. I then glued the Arduino Uno onto the back of the breadboard, directly behind the second button. Then I went on to wiring the triple-axis accelerometer and gyro breakout. I first connected a wire from the ground pin on the sensor to the 3.3 volt pin on the bottom header. This simply provides a 3.3 volt current to the sensor. The sensor then takes this voltage and splits it among 2 parts, the gyroscope and the accelerometer. The gyroscopes work by a tiny piece of mass inside of it which slides around and sends a specific serial data depending on the movement, while the accelerometer works by tiny crystals which are stressed and therefore allow a specific amount of current through depending on the amount of stress, and they send another specific serial data entry with these readings. I then connected 2 wires from the SDA and SCL pins on my accelerometer to the center of my breadboard. Next I put 2 wires which I wired to pins A4 and A5 on the bottom header. Pins A4 and A5 are what allow you to communicate with 12C and TWI pins. In simpler terms, this is where the accelerometer and gyroscope output their serial data to be received by the Arduino Uno and manipulated by the code. I then connected a wire from pin 2 in the top header to the INT pin on the sensor. This is how the button interrupt is able to tell this sensor to calibrate itself. When the button interrupt happens, it sends a specific serial data entry which the code recognizes and tells the accelerometer to zero itself out to get ready for the next swing. Finally, there are 2 jumper wires connected from pins VDD and VIO to ground on the top of the board. This is how the sensor releases the current sent in from the Arduino Uno. After completing wiring for the accelerometer and gyroscope, I then moved on to the wiring for just the accelerometer. The other accelerometer, unlike being glued on the breadboard, this is attached by 6 freestanding wires, 4 of which are used for power source and output. The last 2 wires are placed on the opposite side of the wires connected to pins A4 and A5, allowing the return of information by the accelerometer. I also have 2 resistors which are placed next to these wires connected back to ground to give it the base current of low. Once I had finished wiring everything, I then attached the breadboard to the bottom of a baseball bat using electric tape and glue. Then I attached the accelerometer to the base of the hitting stick and taped the wires together so they aren't all over the place when the batter is swinging. And voila, the physical product has been made. Thanks to Jeff Rauberg and the 12C development team, the coding was a lot easier than I expected. I was able to go to their code libraries and pick out some of the major coding that had been done by them and use it to my advantage. Therefore, I only had to make slight and moderate changes to the code. In this project, I did not want the acceleration or rotational velocity when the ball is hit, but rather the velocity of the bat and angle. In order to achieve this, I had to integrate the values outputted by both sensors. Therefore, every 0.1 seconds when the bat is being swung, the program reads the values of the x and y rotational velocity of the bat and adds that value to an integer. We read it every 0.1 seconds because this seemed to be the sweet spot, allowing us to capture the most data while also not causing the program to hang and freeze most of the time. The x, y, and z values of the accelerometer on the wooden base are also read at the same time as the gyroscope, and these values are added to a different variable. The negative values of the accelerometer are ignored and not added to its variable, since this is when the contraception is swinging back due to the rubber bands. And right now we only want the acceleration moving forward. In a 5-second period, we read data from the accelerometer and gyroscope 50 times. After the swinging phase has ended, we know we have 2 variables, the total acceleration and the total rotational velocity. Next, in order to complete the integration, we multiply these variables by the time, which in this case was 5 seconds. Now we have the velocity of the ball when it's hit, as well as the angle at which it was hit in. From there, we can simply plug into projectile motion equations to get analysis about the swing. Thanks for watching my how-to video. I hope you enjoyed it.